Alright, so in this lesson we have a little bit of review going on, I guess you could call it. We're working with linear functions again. What we're supposed to be doing in this lesson is writing equations for different sets of information. So you're going to see things where we have to kind of pick the best line of fit, and you'll see that over in your core vocabulary there to your left. You'll also see equations where there's a line given and some information about that line, and you're supposed to write an equation given the following information. So one thing to keep in mind here is we will need to know the following formulas, and I would also even throw in that you need to know slope formula. We have slope-intercept form here. We have point-slope form here, and not a lot of students remember that. But it's going to help us kind of make short work of some of these if we know that formula. And then and also this formula, I would argue that you need this one a little bit. This is just slope formula, not slope-intercept or point-slope, but slope itself. We have y2 minus y1 over x2 minus x1. And again, we should know that the definition of slope is rise over run. So we're talking about the steepness of our line here in this lesson. We'll see a lot of different things really, and towards the end of the lesson here I'm also going to refresh your memory on linear systems. Our next lesson really deals heavily with that, so make sure you guys take some notes on that as well. Hopefully this lesson, though, itself wouldn't be something that we get too tripped up on. We'll go ahead and continue on into our lesson here. So if we look here at example 1, as I get it kind of fit here on our screen so that we can see it a little bit better, let's look like that. So if we look here at example 1, we can see that we have a problem here of fuel depleting from a gas tank the farther you travel. The one thing to keep in mind here is that we can see pretty clearly where our line crosses the y-intercept. These lines are going by 2, so it looks like 2, 4, 6, 8, 10, 12 appears to be the gallons that this tank is holding. So we'll keep that in mind. Again, slope-intercept formula looks like this: y equals mx plus b. And the one thing we'll keep here in mind is that our y-intercept there looks like it's 12. Okay, the other thing that we have here is a rise over a run. So if I look at this, a lot of students sometimes space this, and it's something pretty common. Both of the numbers here are positive, so we don't really associate a negative number in here very often. But if I look at this, again, I don't like to look at it like this, and then I don't like to look at it right 90 and then down 3. We like to look at it as rise over run. So if I were to look at this, I would look at it as a rise of -3 and a run of 90. So if I were to write that as a fraction, I would have -3 over +90. Now, again, whenever we're working with slope, we always want to reduce. So a rise of -3 over 90, we can reduce that to a -1 over 30. And I'm going to go ahead and, again, you don't really need to do the slope formula here, but that's your slope. And then if we look up above at the work we found from before of the y-intercept, we can write an equation just by looking at this picture and not really having to dig too deep into it. And we have -1 over 30 x plus 12. So that's pretty easy, and we can see there that it makes sense. For every for every 30 miles that I travel, I'm losing a gallon of gas. So that's again how you can find the fuel economy of your car, and then also how big of a gas tank your car has. It's a pretty common real-world example of how you would use slope in figuring out the fuel economy of a vehicle. So that's something that's kind of neat there for their practice problem. Here's one that's slightly different. It seems as though you can maybe probably assume and guess what the y-intercept is, but with our units of measurement vertically, the volume here in cubic feet is measured in hundreds. I'm not gonna just take a shot in the dark here and assume that I can be exactly right. Instead, again, at the very beginning of the video here, I gave you slope formula. I'm gonna be a little more precise with that. So first of all, I'm gonna use my slope formula to find my slope. So I need to take the y's and subtract them over the x's. So I'm gonna say 300 minus 180 over 3 minus 5. And when we do that, we get 120 over negative 2. And we can reduce that down to negative 60. So now here's where our point slope formula comes in handy. And again, if you don't recall that, really all you're doing is you're taking slope formula and you're getting the y's over on the other side. So point slope formula is y2 minus y1 equals the slope m times x2 minus x1. So we have enough information here to do this because we have a slope and a point. Really, and this is kind of nice, we don't have to put values in for the y2s. We only really need one value. So what we're going to do is call slope formula something a little bit different than point slope formula and take values off so that we have an input variable and an output variable. And then what we can do is transition this into writing it into slope-intercept form that is a little more familiar to us. So y equals mx plus b. So now that we have this information over here, let's plug stuff in. And it doesn't matter what point you pick. We're going to end up having to reduce and get a little bit of stuff cleaned up as we go anyway. So let's just use that top point. We'll say y minus 300 equals, the slope is negative 60 times x minus 3. Now we're going to, like I said, we have got a little bit of cleaning up to do before we can make it look like slope-intercept form. So first we're going to distribute y minus 300 equals negative 60x plus, we have 180 when we multiply that through there. And then I'm going to add the 300 to both sides. So now we can get our slope-intercept form answer. Y equals negative 60x plus 480. Now, if I take this answer, and again, this is my final answer here. If I take this answer and I go and look and approximate on my picture about where that should intersect, 480 looks pretty reasonable. If I go through on a problem like this in the homework or on a quiz or test, whatever it may be, and I look at my picture that's given and see that it's nowhere close to where it should be over here, you guys can hopefully see that that doesn't really make sense and get that adjusted and fixed so that you guys have a more reasonable answer. But again, there's a problem like one that you'll see. Line of fit is a little bit more challenging, and we're getting to that. When we do line of fit, well, I'll just discuss it when we get there, but when we do line of fit, we'll be able to use some tools to our advantage. Sorry, I'm having to zoom here. I'm trying out a new thing for my videos. There we go. So again, line of fit looks a little bit different. We're going to use some tools for that, and I'll show you those in class. We have all kinds of resources out there. Your textbook shows you an example of using a graphing calculator, and I don't know how many of you guys have those, but there's tons of great resources on the iPad, and I'll show you a couple of those in another video here. So the next thing we're going to talk about in this video is solving a linear system using substitution. Now, we're going to get into some pretty intense problems in our next lesson with 3 variables, so they figured in this book that they would refresh your memory using just 2 variables. And here's how this works. When they do this, we have to isolate a variable. So when we're substituting, our first step is to isolate a variable. If it's already done for us, and you guys can see that very clearly it is in this problem, our x variable in our bottom equation is isolated. Once we have that done, then we take some information that we know about that variable. We know that x is equal to 4y minus 1, and we take that information and we plug it in for x in our other equation. Most of the time, students kind of pick up on this after a while, but it does take some refreshing. So I'm going to copy down the formula up above, except for the x is no longer x. It's going to be 4y minus 1. And then the rest of the formula is copied down exactly how it's written up above. So now when I go to solve for a variable in this new equation, I only have one variable to solve for. Now I have some work to do and some combining of like terms, but I can do it. I can't solve for two variables. So now I'm going to distribute 8y minus 2 plus 2y equals 3. We combine our like terms. 10y minus 2 equals 3. We add 2. We get 10y is equal to 5. We divide by 10, and we get y is equal to 1/2. Now, the tricky thing is to remember that we're not done here. We have to solve the linear system, and when we're solving a linear system, your answer is always a coordinate point, x comma y, unless it's not possible to solve. So with this problem, now we have a little more work to do. We need to take the fact that we know y and go ahead and plug it back in for y up in the equation. And I would just pick the one where x is already by itself. So when we do that, again, we don't know what x is still, but we know that y now is 1/2. So again, the book is forcing us to use some fractions here, but this one's not too challenging. We have x is equal to 1/2 times 4 is 2 minus 1. X is equal to positive 1. So my overall answer of this whole thing would be 1 comma 1/2. Now we have another problem that's pretty similar, except for now this time we're not going to be substituting. We are going to be eliminating. Again, our end result ideally is the same. With this one, when we go to eliminate, before we can do something like that, we have to have either the x coefficients or the y coefficients match up. Now, typically, if I'm going to solve a problem like this, I'm just going to end up plugging in and solving for y in the bottom equation and plugging it in and solving by substitution. But I want to show you guys one by eliminating. So if I want to solve this one by eliminating, I first need to get my coefficients the same, and let's just make our lives easier. Let's multiply this top one by a negative number so that the signs change, and I'm going to multiply it by -4. And when I do that, my new equation for the top line is going to be -2x minus 16y equals -16. And again, I did that by multiplying all of these terms right here by -4. Then I'm going to copy the bottom one down exactly how it's written. 2x minus y equals 14. Now, if we look at this, when we go to combine these things, my signs are already different for my x's, so I can just add. I can do it like it says. -2 plus 2 goes away. 16 and y have the same sign, so we're going to add them up and keep that negative sign and get -17 y equals -16, and 14 gives me 2. Just because I'm running short on time, and also I think your textbook did something kind of screwy to me, and I feel that there's supposed to be a number there, I'm going to kind of wrap this one up by just kind of explaining what we do. So again, we finish isolating our y here and get -17. And again, I'm not going to have you guys do this one in the homework, but we end up with our value for y. And what we do after we find y, this can't even be reduced. So again, I'm almost certain that there's something fishy going on and it didn't copy for me here. But once we get here, we just take this value for y and we plug it back in either here or here. So again, it would be something like this. It would be like 2x minus negative 2 over 17 equals 14. And then we would combine like terms and do all that jazz. So it would end up being, and I always tell my students, so I am going to go through this step with you here real quick. When I go to solve this, rewrite that as 2 plus 17 before you move it over so that you know and understand that your correct order of operations to move it is not addition, it's subtraction. Other than that, again, I've got a crunch to get inside of 15 minutes here, guys. So hopefully this was helpful. Again, we'll go through further questions if we have them in class, but good luck on this.